In one of the previous lectures, we were saying that if we are given Lagrangian and if we put it in Euler-Lagrange equation of motion, then it will give us the correct equation of motion. Once we get the equation of motion, we should be able to conclude what type of motion it is. For example, if we get q double dot equal to 0 as the final equation of motion, then this means that there is no acceleration, and there is no acceleration means there is no force, and this implies the particle is free particle. Similarly, if the final equation that we are getting after putting the Lagrangian we have in Euler-Lagrange equation, if the final equation of motion we are getting is q double dot equal to minus omega square q, then this is simple harmonic motion. This can be written like this as well, minus kq. Here k is a positive quantity. K is positive quantity. Now suppose the final equation that we are getting is q double dot plus 2 gamma q dot plus omega square q equal to 0. This is representing damped oscillation. If q double dot equal to minus k times some function of q, then this is oscillatory in nature if f of q is odd and non-oscillatory if f of q is even. Another equation that we can get is theta double dot plus g by L sin theta equal to 0. This is the equation of pendulum, and this is non-linear and it is not as simple as it is. But if oscillations are smaller, then we can approximate sin theta to theta, and then it will become a simpler problem. Now let us say the final equation that we are getting is q double dot is equal to minus omega square q minus alpha q cube. Then this is representing an harmonic oscillator. What we are discussing here is how to conclude the type of motion from the given equation of motion, because sometimes in the option there will not be any mathematical equation, there will be only language. Therefore it is necessary for us to be able to understand the type of dynamics from the given equation of motion. Now let us discuss conversion of Lagrangian to Hamiltonian. So we are given L, we need H. We can use the relation H equal to summation pi qi dot minus L. H is a function of q, p and t, generalized coordinate, generalized momentum and t. L is a function of generalized coordinate, generalized velocity and time. To convert Lagrangian to Hamiltonian, we use the following steps. First of all, we will find the generalized momentum pi is equal to del L upon del qi dot. Then we will solve for, from here we will solve for qi dot. Qi dot is equal to, as a function of q, p and t. Then we will substitute this qi dot, which is written in terms of q, p and t, it will be substituted in h equal to this equation. In equation 1 we will substitute qi dot value. Here we have to substitute. Also in the Lagrangian we have q dot t. Here also we will put the value of qi dot. Once we do that and simplify, we will get Hamiltonian as a function of qp and t. Now let us do an example to get more clarity. Let's say the Lagrangian we have is half m q dot square minus half k q square. This is the Lagrangian of a simple harmonic oscillator. Now we want to find the Hamiltonian. We want to convert Lagrangian to Hamiltonian. The first step to do that is we will find the generalized momentum. P is equal to del L upon del Q dot. This is equal to m Q dot. From here we will solve for Q dot. Q dot is equal to P by m. Now we see that Q dot is written as a function of Q, P and T. Q dot is equal to P by m is a function of Q, P and T. Now we will substitute Q dot in H. H is equal to summation Pi Qi dot minus L. There is only one coordinate, so there is no need of summation. It will be simply PQ dot minus L. L is half m Q dot square minus half KQ square. This is equal to PQ dot minus half m Q dot square plus half KQ square. Now you will put the value of Q dot is equal to P by m in the H. P times Q dot is P by m minus half m Q dot square. Q dot square is P by m the whole square plus half KQ square. This is equal to P square by 2m. From here we will get P square by m, and we are subtracting P square by 2m, then we will get P square by 2m plus half KQ square. So this is the Hamiltonian that we obtain corresponding to the Lagrangian half m Q dot square minus half KQ square. You can see that in the Lagrangian half m Q dot square, it is converted to P square by 2m in Hamiltonian, and minus half KQ square is converted to plus half KQ square. Before proceeding further, let's discuss a problem which will help you to revise a concept that we discussed in the previous lecture. Revision is important because what goes into your brain is less important than what stays in your brain, right? The question here is from NET December 2019. To solve this question, we can make use of gauge transformation of Lagrangian. So when we have a Lagrangian and when we add some function f to the Lagrangian and we obtain a new Lagrangian, then to decide if the equation of motion changes or not, we do a couple of steps. First of all, we will check if f is a function of q and t, q dot and t. If it is, then we will try to write f as total time derivative of some other function which is the function of q and t only. Now in case if f is a function of q double dot t, q dot t, then in that case we will check if d square upon dt square del f upon del q double dot minus d by dt of del f upon del q dot plus del f upon del q is equal to 0 or not. If it is equal to 0, this implies equation of motion does not change. otherwise equation of motion will change. So in the option A, we have a function f. This is a function of x double dot and y double dot, x and y. Therefore, we will use this condition, d square upon dt square del by del q double dot. Q double dot here is x double dot. F is x double dot minus y double dot minus d by dt of del by del x dot x double dot minus y double dot plus del by del x of x double dot minus y double dot. We are checking if this is equal to 0 or not. So from here we have d square upon dt square x minus d by dt of 0 plus x double dot, which is equal to x double dot plus x double dot, which is equal to 2x double dot. So this is not equal to 0. This is not necessarily 0. Therefore, equation of motion can change. Equation of motion can change. Now let us consider option B. In option B, we have xy double dot minus yx double dot. Again, this is a function which is including double dots. Therefore, we will check again if d square upon dt square del by del x double dot xy double dot minus yx double dot minus d by dt del by del x dot xy double dot minus yx double dot plus del by del x xy double dot minus yx double dot. This is equal to minus y double dot minus 0 plus y double dot, which is equal to 0. Therefore, equation of motion does not change. Option B is the correct answer here. Now you can check option C and option D as well. Option C is a function of x dot, x, y and y dot. Therefore, we use the first condition. We will try to write this f as total derivative of some function of x and t only, x, y and t only. But we will not be able to do that. Here also we will not be able to do, because x dot is squared and y dot is squared. It is never possible to write this as a total time derivative of a function of x and y and t only. A good response from your side is the motivation to do more videos like this. See you in another lesson. Thank you.